Hello and welcome back to Calculus 1, section 4.2 on mean value theorem. Mean as an average, not mean as an evil. So let's clear that up first. So we talked about the difference between average and instantaneous, and we understood that they are not the same concept. Average was taking all of the values across the board and equating them, putting them in the same equation, right, and coming up with the number at the end, where the instantaneous was the value of change in the instant when we observe. The way I described the difference between average and instantaneous was the velocity, where you calculate your average speed after you are done with your trip. You take the amount of miles you covered divided by the amount of time it took you to cover that amount of miles, and you find the average speed in miles per hour. So that was the average speed, and you had to be done with the trip because you need how far you went and you need how long it took you to go there. So now, instantaneous one is the one that your speedometer is displaying at all time. As soon as you touch either a brake or a gas pedal, it changes its value because it measures the velocity, it measures the speed of an instant. So that's the one that you get using the derivative. So average one is the one where you use your, the average one is where you use slope of the secant line, which is the basic algebra, and the instantaneous one is when you use calculus with a difference quotient, or a limit of a difference quotient, to come up with the slope of the tangent line, which measures instantaneous change. Now today we're going to take a look at a situation over here and see. So let's say this is a stretch of a highway. We'll put you in a car right there. Going this way with a speed limit of 60 miles per hour. I'm going to put some shrubbery over here. And we're going to put another car right there. There we go. Then, a couple of miles down the road, we are going to have another shrubbery, like so. There's going to be another one of these cars. All right. Do we all understand what's happening here?
Traffic.
Yes, you are driving down the highway, and there is a speed trap right here, and there's another speed trap right there. Let's say that these two are, 10 miles apart. Okay, so they're 10 miles apart. The speed limit is 60 miles per hour. And since you invested in the radar detector, because you were told, yeah, it's $400 to buy it, but the first time it goes off, it paid itself off, right? You said, all right, fine. So you have one of those things. You're driving around and it beeps as you are approaching the first trap over here. So you drive through the first trap exactly 60 miles per hour. You are not pulled over, right? And let's say you passed at 3:08 p.m. through that trap. So that's you going through the first trap, and because you had the radar detector, it alerted you of the trap. You have the exactly speed of 60 going through it, so that's all good. Now you are approaching the second speed trap, and for the second time, the radar detector alerts you that you will be passing by the speed trap, so you slow down, let's say you were going over, to 60 miles per hour, and you pass through the second speed trap at 3:14 p.m. You are not pulled over because you were going exactly the speed limit, and you just drive off. All right, fine. So now what happens? A few days later, you get the ticket in the mail. What? Now at this time, usually when I have so many students in the class, I just ask you, did anyone get the speeding ticket in the mail without being pulled over?
I got that red light camera when they had those.
Yeah, not the red light, speeding ticket on the highway. Huh, strange. There's a lot of you, so the chances are that you will get one, but that's okay. All right, so, or person doesn't want to identify, it's okay. Usually when I have, about 30 of you in class, I was like, oh yeah, or oh I know, or my mom did get it, or something like that. Anyway, that's fine. So, a ticket? I went through both of these at 60 speed limit. I was never pulled over. Like, what? Okay, let's see. The trick is that these guys were not tracking your speed. I mean, they're tracking the speed, obviously, but they were also tracking who's passing by. So what do we know about the average speed? We know that the average speed is going to be distance divided by time. The distance is 10 miles. And the time is 6 minutes. Time is 6 minutes. Okay. So I need this in miles per hour. So I'm going to cancel the minutes with hours like this. So 1 hour has 60 minutes. And oh, this is terrible. When you cancel minutes and minutes, you get 100 miles per hour. That's your average speed, okay? Remember that you slow down to a 60 for some time to go to the traps. It's terrible, but there you go. What we are going to learn today is the formula that connects average to instantaneous and why they can issue tickets like this without pulling you over. And then the way it's implemented. So what do? Well, if you understand the way that average works, average is the average of all instantaneous speeds that you have. So if you have a speed of 0 at the beginning of your trip, if you have a speed 0 at the beginning of your trip, and then you speed up, and then you slow down, and you speed up, and slow down, and speed up, and then you have to stop for the, let's say, red light or something, and then you speed up again and you drive, and you just have to stop again because you reach your destination. Right? This is what the graph of your speed looks like, because you catch up with the traffic, you pass the traffic, you stop on a stoplight or a red light, stop sign or the red light, and then you keep driving and so on, and then eventually you end up stopping because you got to school or whatever. All of these speeds are the black lines, the black dots. They are all instantaneous, and then they all average into a single red value here, which is velocity average. But the cop is going to give you a ticket when you are over speed limit on any of these locations. It doesn't matter where, right? Any of these locations that are higher than the speed limit, is higher than the average, because generally, you will work out the average, which is around the speed limit. So the concept from calculus that we explore in this lecture is called the mean value theorem, which is the one that connects the world of average to the world of instantaneous. In this case, the world of black and the world of red. And those have completely different formulas. The world of red has the formula of the slope. Slope of the secant line is going to be f of x2 minus f of x1 divided by x2 minus x1. So this is technically your basic algebra slope, y2 minus y1 divided by x2 over x1. Now instead of using y1 and y2, we use f of x2 and f of x1. Right, that's it. And the world of black, in this case on the graph, where you have the m tangent, which was the limit of m secant, and that was the derivative. Right, so, and that's the instantaneous. So these are the two worlds that we have, and we understand the difference. Hopefully by now, this is lecture number 3 that talks about it, or maybe 4, the difference between average and instantaneous. Now what we want to learn is it's not a definition, it's a theorem. We want to learn the mean value theorem. So, if f is continuous on closed interval a, b, so if f is continuous on closed interval a, b, and differentiable on open interval a, b, then there is at least one point C in AB such that, and here's the formula, f prime of C is equal to f of B minus f of A divided by B minus A, which is our interval. This is our formula for mean value theorem, and as you can see, it is the formula which connects the world of instantaneous, which is the derivative, with the world of average, which is the slope. You cannot get ticketed for your average speed, because average speed happens over a period of time, and we see over there on that, which is the black line, right? We see that your instantaneous speed is the one that goes up and down, up and down, up and down. The average speed is always the same, and that average speed could be, let's say if the speed limit is 60, if your average speed is 59, then you can't get ticketed at all, even though there were instances that you were going 85, 90, right? You also saw the example that I put up there. I could have used better numbers. We can adjust it, but where the average speed was 100 miles per hour. The average speed was 100. So this car might have been going 120 at some point, right? Passed through both speed traps at 60, right? And it's at the end the average, right? But
how do they do that? They tag your license plate, or?
So how do they do that? How is this used?
Legally.
Legally, yes. How is this used? Easy pass gates. Yeah. You see, easy pass gates are on a certain distance apart. And you have your easy pass tag that is tagged to your driver's license, your credit card, your name, your car, your everything. So when you go to the first easy pass, it's logged that Jim went through the first easy pass at this time. You go to the next gate, there you go, finite distance, right? And all they need is how long it took you, right? Because that's the only piece of information. You see, this 3:14 over here makes it 6 minutes later. That needs to be 13:18. 13:18 is 10 minutes from 3:08, 10 minutes in 10 miles, minute per mile, 60 miles per hour. So now that obviously cannot just say, okay, no more cops, because what you can do is you can drive between two easy pass gates at 200 miles per hour, park your car, wait till time is right, and then just pass through, right? You go, it's like, what's the purpose then?
To do it.
Have two accounts?
Yeah.
Oh, I see. Okay. Yeah. Okay.
Where did he come from? Where did he come from?
It's magic. Yeah. So that's how we use calculus to catch criminal drivers, which all of you are.
What? But regular cop cars, they don't have that technology where the radar just detects your speed and they can't average
That's
out
it. Yes. It's easy pass gates, and they were also thinking about implementing the whole bunch of other stuff and make just the speed gates and all of these kind of things, because it's a zero issue just to keep sending tickets.
I know in the UK on the big motorways they have that, so I'll have like sections of the motorway where the speed is checked.
Yes.
They have cameras and they tell you that they're checking the speed, but they still go and they'll have cameras at different points on the motorway.
Yes. So depends on where you are. I am not sure where the development is. I mean, everything starts in. So you get just a ticket mailed, because here it is, the formula that said the average was the same as at least at one point in time. So if you go back to this image over here, right, and if you're this lousy example with 100 miles per hour, but this is where the 100 miles per hour is. Now look at these peaks over here, right, and this one over there, and this one over there, right? These peaks are all 110, 120, 130, right? So they can ticket you for 100 because it's guaranteed by the math that the average that you get, which was 100, the average you get there was 100, is going to be equal to at least once for 2 instantaneous, which is what is ticketed. And that's it. So now we can just do few extra examples, a different situation, and this lecture is over. There's one formula and one. There is another concept which is used to prove this, but we don't have to worry about it. It's not the honors section, so we can skip on it.
Can you go back up real quick to the formula?
Back up real quick. There you go. So you said real quick.
That is true. For like 20 seconds.
13, 12, All right. So if the function is continuous, and I like to think about conditions, because on the exam, if I am to ask you to state mean value theorem, a lot of students just write the formula completely ignoring the text. Text is important. Mean value theorem doesn't apply on problems that are not continuous, because teleportation, right? If you teleport from location to location, well, there's no speeding ticket there, right? So it needs to be continuous. You can't be driving, down the highway 100 miles per hour, your radar detector goes on if you teleport, right? Out of the speed trap on the other side and you move, right? You see the idea, continuity, right? That's where the continuity kicks in. What it means differentiable. Differentiable means that you actually have the speed. Remember, the derivative of position, which is you roaming around, is the velocity, right? Velocity is the derivative of the path, of the displacement. So the derivative must exist. That means that you have the velocity, you are moving. So technically, these two things make sure that you exist and what you're doing exists, right, in the real world, right? Between the 2 points A and B, which are the two values on X interval, because you are going from point A to point B. So that stuff there. And then the math, the third line over here is the math line, which is the one that connects the two worlds through this point C that is in between, at which point you actually make those two speeds to be the same. Now, before we do another applied problem, let's just do some of the boring math problems that have no purpose, it's just calculation. So, this one over here says find C, done. Find C. What?
I found C, it's right there.
Oh, right here. Okay, good. Where's Waldo? Find C, and the spec on the problem is f of x equals x over x plus 2 on the interval of -1 to 2. This is it. This is all you need. There is some kind of a function, f of x, and there's the interval from x1 to x2, and your value c needs to be between these two numbers. But hold on. You don't get to do any calculations before you check that the conditions apply. You see, this function is not continuous, right? And we need the continuity. Where is this function discontinuous?
0.
-2, right? When the denominator is 0. That's what you meant to say. Yeah. So when the denominator is equal to 0, the function is discontinuous, and that happens at -2. Do we care? No. -2 is not in our A to B, right? So let's say you have to drive to school, and you are using the road that doesn't have a broken bridge on it. Do you care that the bridge behind you somewhere is broken? You don't. That's clearly a discontinuity in your path to get somewhere, right? But because it wasn't on your path, it happened outside of your path, you don't care that there is a broken bridge 3 blocks down your street. They're fixing it. You can't use it, right? So discontinuity is something that you have to pay attention to, but then that discontinuity might not be in the interval you care about, so we don't care about that discontinuity. So you have to start there, because if this interval was from -3 to 2, there will be nothing for you to compute, because the condition for the mean value theorem would be violated, which means theorem does not apply, and you move on to to the next problem. Okay, but in this problem, discontinuity is at -2. -2 is not in our domain that we are considering. Good. Is this thing differentiable? Well, again, the same deal. It's not differentiable at -2 because there's a vertical asymptote. But still, we don't care, right? Because -2 is not in the domain and so on. So this is where we are using what we defined long time ago as the piecewise continuity, right? There is a piece from -1 to 2 where the function is continuous. We're happy. We're using that piece so we can do the problem because it passed both conditions. So step number 1, conditions, continuous, check, differentiable, check. Woohoo. Now we can do the problem. Now we are supposed to use this formula. You are supposed to find the derivative of the problem and plug the unknown c into it. And on the other side, you are supposed to plug in your limits a and b, right, which are -1 and 2, into the values and compute everything. So we need f prime. F prime of x is, well, that's a quotient rule over there. So you can use x plus 2 squared. Then we have x plus 2 times 1 minus x times 1. Simplified to x plus 2 minus x divided by x plus 2 squared. Altogether 2 over x plus 2 squared. There's the derivative. So now we have that the function is x over x plus 2, and we have the derivative is 2 over x plus 2 squared. So now we say f of c, f prime of c needs to be f of b minus f of a divided by b minus a. We know that a is -1, b is 2. So now we plug everything in. Instead of f prime, I'm using the formula, the expression we got. So that's 2 over c plus 2 squared. F prime of x is in terms of x. F prime of c will be in terms of c, and I'm looking for that c. So it's 2 over c plus 2 squared equal to, now, f of b. Well, that's my regular function f. Regular function f is x over x plus 2. So 2 over 2 plus 2 minus -1 over -1 plus 2 divided by b minus a, 2 minus -1. I plugged in b, which is 2, into f of b, and then I plugged in -1. And as you can see, this equation has a single variable, which is variable c. So we just compute that. So I have 1/4 plus 1 divided by 3. 2 divided by c plus 2 squared is equal to 1/4 plus 1 is 5/4 over 3. This simplified is 5 over 12.
That'd be 1/2.
What we won't have?
2 over 4.
It clearly is 1/2. I'm not sure what you're talking about, but this is a half over here. Yes, thank you. Please pay attention. So 1 plus 1/2 is 3/2. And we have 3 over 1, so now these 3's will cancel and you get 1/2 for everything. There we go. Better. So we have 1/2. Okay, great. And now to solve this equation, just cross multiply. C plus 2 squared is equal to 4. Square root both sides, you will get C plus 2 equals to plus minus 2. Usually people forget plus minus when they square root because they're noobs. But you won't do that, obviously, because you know. And now we're going to subtract 2 on both sides. So C is either going to be 2 minus 2, 0, or C equals negative 2 minus negative 2 is 4, which we dropped because it's not in the domain. And the only value we care about is this one. And we make the conclusion that at C equals 0, which is x equals 0, C equals 0, we have instantaneous rate of change and average rate of change to be the same value. So that's where they match. All right, since this one was so much fun, let's do another one, and then we'll do the word problem. And then we're done with this. What should we do? 19, 20, 21. Any takers?
21. Oh, is that the harder one?
No, it's fine. Find C. F of x equals sine inverse.
I do my part.
Sine inverse of x on 0 to 1/2. I'm trying to do my part. You know the steps. Figure out the derivative, plug the values in the original function, figure out the numbers. Sure, why are you guys putting that? I know that we said inverse sine and inverse tangent will be the ones you know. For inverse cosecant, it's okay with the table. But this one kind of hurts.
Don't take it personally.
No, I mean, don't take it the wrong way. You need to know that. Once you have the derivative for the function, plug in C equivalent to f of b minus f of a. So, wonderful exercise. Exam grade question. Still here. Four o'clock. Wait, hold on. You can X-ray that. The heritage.
I should know.
Do you recognize the letters? Or you don't know?
I can't read it.
Oh.
So what were you planning on saying?
Well, I was told I wanted to put this in leadership. So I said, okay, because of very specific leadership roles, because I will structure the company. So it will be interesting to learn about pressure, all the things that will happen. So I have a presentation for that. That's what we used to do, that's what we were trained to do. And then they turned out it's like how education is doing. So we was like, it doesn't. So I had to scramble. Yeah, I mean, if I tell you,
Yeah.
but I had to restructure everything. And they sent me the last night, so I had yesterday and this morning, and I only had an hour and a half this morning. So I was literally teaching the car, while I had the other class, of how I was going to my way out of it, because whatever they want me to say is not
What you want to say, yeah. Well, you started saying that towards the end, you're like, well, I don't know if my opinion is going to be listened.
But tomorrow, right? They're opening up a so I contacted my mom to get all of the stuff that's still in my apartment. And they contacted my sister to bring the right road for me to be there so a bunch of my friends. And there will be video clips that I have. I actually have video I downloaded
Of what was going on.
Yeah.
I remember you saying you would YouTube it, right?
I have some of them include me and some don't include that. Some look like the camera, some look like participating in stuff. People speak to see it, but then it was so much undertaking.
The guy that was there over the team. About the burning barrel. The barrel, the name, okay, the name was wrong. But you throw money in it.
That's what was so curious.
Yeah.
You get more angry when something is constantly fun, and when someone touches your face,
Oh, yeah.
because when someone touches your face, it's not fair.
What can you do?
So that's why I'm so cool. We're trying to use myself quite
Let's take a look at this problem together. Are we good with continuity? Well, inverse sine of 0 is 0. We're cool. Inverse sine of a half is pi over 6, so we're good. All right, cool. What's the derivative f prime of x? Very good. Glad that you know that one. And now we are going to come up with the f prime of c. Well, actually, let's do it this way. F prime of c is 1 over square root of 1 minus c squared. All right, so now we say 1 over square root of 1 minus c squared, that's the f prime of c, needs to be equal to f of b, that's sine inverse of 1/2, minus sine inverse of 0, divided by 1/2 minus 0. 1 over square root 1 minus c squared is equal to inverse of 1/2 is pi over 6 minus 0 over 1/2. So these guys will cancel down to 3, and we have pi over 3. So now you have equation 1 over square root of 1 minus c squared is equal to pi over 3. So all you need to do now is to solve this, and you're done. Well, just cross multiply, come on. 3 equals pi square root of 1 minus c squared. So the square root of 1 minus c squared is equal to 3 over pi. Square both sides to kill the root. You get 1 minus c squared is equal to 9 over pi squared. Then get c squared alone. So c squared is equal to 1 minus 9 over pi squared. And then square root both sides, and don't forget plus minus, to get that c is equal to plus minus square root of 1 minus 9 over pi squared.
Why is it minus 9 pi over 2? If you're moving it over, shouldn't it be...
You move it over, it becomes negative. You move c over, it becomes positive. And then I swap the sides. What happened? Well, we can do just a little bit better, right? Because we have this nice pi squared in denominator. So this is going to be plus minus pi squared minus 9 over pi squared. And we can kick out plus minus 1 over pi square root of pi squared minus 9. And now we're done. You cannot take the square root here because of the minus sign. Do not play with fire. That's illegal. So plus minus 1 over, actually what we can do is we can say plus minus square root of pi squared minus 9 divided by pi. That would be the value at which the instantaneous and the average values are the same. Let's find a word problem to have more fun. Mean value theorem and the police. That's not it. The next one. Mean value theorem and the police again. Yes.
Can you explain how you got the pi, how you changed it from pi squared underneath and pulled it out? Oh, because you take the square root.
Take some of the circle.
Okay.
You're welcome. No, you did the work. Thank you. Good talk. So we did the problems with the police. Verify that the functions tangent squared and secant squared have the same derivatives. what can you say about the difference f minus g? That's a nice problem for honors section. Let's go. So we have f of x equals tangent squared x, and g of x equal secant squared x. Verify that they have the same derivatives. Go on, I'll wait. Right. Now, do you have the derivatives? It all looks cool, which is basic chain rule, right? So you see that the derivatives are the same. They're asking, since derivatives are the same, what can we say about the difference of functions? See? So they're not asking about the difference of derivatives. Difference of derivatives clearly is 0 because it's the same thing. They're asking what you can say about f minus g now that you know the derivatives are the same. It's constant. Very good. The difference between those is constant. And you can call it constancy. We know what it is because it's a basic Pythagorean identity for trig. But the answer is it is constant. That's the best answer you can give. Now, what we know is that tangent squared x minus secant squared x is equal to 1. We know this because 1 plus tangent squared is secant squared when you rearrange it. So it's a basic trig identity, actually. So we see the two derivatives and the difference of two derivatives is 0. That means that the difference of the two derivatives, if the difference of the two derivatives is 0, so it's a kind of cool problem. And here is one example about the running. It says Usain Bolt, a Jamaican sprinter, set the world record of 9:58. So 9.58 seconds. I'm not sure why it's called Bolt. That's not as fast as lightning, but that's okay. Lightning goes speed of light. And 100-meter dash. Did the speed ever exceed 37 kilometers per hour? Did the speed ever exceed 37 kilometers per hour? What should we do? They are asking about the speed of 37 kilometers per hour. Is that instantaneous or average? Which one is inferred over there? There's a 50-50 shot. It's instantaneous because you want to know the instant speed. Did you ever got, even for a split second, to 37? So that's the instantaneous. You can calculate the average from the info you have on the left and see what it says, and if 37 is, if you reach 37 with it. So we have our distance, 100 meters. We have our time, 9.58 seconds. Convert this into kilometers per hour. It's metric. So the speed is distance over time. I need to deal with seconds. I need hours. 1 hour has how many seconds? Very good. And then I need to deal with the meters into kilometers. 1 kilometer has how many meters? Excellent. So now we cancel everything we can. Meters cancel meters. Seconds cancel seconds. So you see that the only units are left are kilometers and hours. Now we can knock off 1,000 with 100 and the extra 0 right there. And all I need to compute on top row, 360 kilometers, and in the bottom row, 9.58 hours. So now we divide 360 by 9.58, and we'll get average, right, is going to be 37.6. Kilometers per hour. Now, what we understand is that the runner starts running at the 0 speed. That's where they are, right in that stance before the shot is fired, right? And as soon as the shot is fired, they start running. So he is starting at the 0, and we don't really know, right? Speed goes up, speed goes down, speed goes up, right? Speed goes down. What we do know is that the average somewhere is 37.6. And they're asking if at any point he was doing 37. Well, of course he did. Because if you have your average to be 37.6 and you started running from 0, that means that at some point you were running over 37.6 to balance out this. And you know what? This runner eventually ended the race and stopped as well. So the speed of this runner went up and down and up and down and so on. So he went at least twice 37. That's elevation for 37, a little bit less than 37.6. So he went 37 kilometers per hour at least twice. So it's a really cool exercise. There's another one of the same. Explain why a runner completing a 6.2 mile race in 32 minutes went through 11 miles per hour. Well, at least twice. So it's the same problem, but this one is done in imperial units rather than in metric. And that is the mean value theorem. You are responsible for the statement and the formula, not just the formula. Your function has to be continuous and has to be differentiable, and then you will be able to work out the mean value theorem. And again, mean value theorem sets the equal sign in between the instantaneous change and the average change. Ta-da! Bye.